we know that if an object is moving in a vertical circle, then it certainly has the potential to stay in that circle, even when it's upside down. We can analyze that problem no matter where the object is, top of the circle, bottom of the circle, side of the circle, or anywhere in between. But we will choose to focus on when the object is at the top of the circle and when the object is at the bottom of the circle. And the reason we do that is because those are the extremes, the extreme forces that are acting on the object. Now, tell me, this is a review of yesterday, right? Tell me which two forces act on both of these objects, no matter where it is in the circle, top, bottom, middle, or otherwise. As long as it's going around in a circle, we have what two forces acting? Yeah, we have the force of gravity, and that's acting down in both cases. When you're at the top of the circle, gravity acts down relative to you. When you're at the bottom of the circle, gravity acts down. Now, what other force do we have as well, Braden? We have the normal force as well. When you're at the bottom of the circle, which way does the normal force act? What is it that provides the normal force, firstly? What is it that supplies it? Like right now, the ground, the floor is supplying the normal force on me. When I'm on a roller coaster, it's not the ground, right? What is it? The track, right? If I'm swinging keys around my head, it would be the rope that was supplying the normal force, right? The tension in the rope that was supplying the normal force. Braden said the normal force, when you're at the bottom of the circle, is acting up. That normal force, when you're at the bottom of the circle, must be greater than gravity, otherwise it wouldn't stay in a circle. If the force toward the center was smaller than the force away from the center, then it would not stay in a circle. We wouldn't have a centripetal force then. Now, when you're at the top of the circle, which way does the normal force act? Which way does the track pushing on you, or which way is the string pulling on you, or whatever the case may be when you're at the top of the circle, Kyle? Which way is the normal force at the top? Ireland, which way is the normal force when we're up here? Good. The track is pushing down on us. Now, we don't know whether it's bigger or smaller than the force of gravity. That depends on how fast it's moving, right? Yeah, Rick.
Why is it pushing down?
Well, if you're at the top of the circle, would you agree that it's the track that's supplying the normal force to you? Okay? Just like it's the ground that's supplying the normal force to me right now. When you're at the top of the circle, where is the track? It's above you, right? So that track must be pushing down on you. Does that make sense? Okay. And it would be the same thing if I was swinging my keys around my head here, like this, in the demonstration that I did yesterday, right? If I swing these around, the normal force wouldn't be supplied by a track, it would be supplied by the string, right? When it's at the top of the circle, which way is the string pulling? Downwards, right? All right, so we're going to say normal force, whether it's string, track, whatever, is acting downwards. Now, you guys told me yesterday that in every case, we say the net force is equal to the sum of the forces, which is always Fg plus Fn. No matter whether you're at the top of the circle or the bottom of the circle, it's the same two forces that act. Now, we also know that F net is m times a, but in the context of circular motion, a is v squared over r. So we're going to say the net force is the centripetal force, mv squared over r, equals Fg plus Fn in both cases. Now, I'm going to pull out the red marker, and I'm going to say everything that we circle in red is going to be a negative value because it's acting down. Tell me something that I should circle in red here. One thing that should be a negative value. Fg, Fn at the top, Fg, Fn at the bottom. What's one of them, Braden? Good. Fg on both is going to be down. The force of gravity is always acting down. So in the context of vertical circular motion, we're going to make the force of gravity negative always. Not until we plug numbers in, but as soon as we sub those numbers in, then it becomes a negative value. Anything else that should be negative, or is that it? Yeah, Bree? Fn at the top should be a negative value because it's clearly, by the diagram, acting down. Good. But not until we sub numbers in for it, right? Anything else that should be a negative value? Is that it? Okay, tell me something that should be positive then. I'll circle positive in purple. Positive because it's upward. Yep. And Fn, normal, the normal force at the bottom. Yep. The normal force at the bottom should be positive because it's upwards. Good. Anything else that should be positive? Okay, it seems like maybe we're having a little bit of trouble with mv squared over r. We can't decide whether it should be positive or negative. Rachel, mv squared over r at the top, let's say, should it be positive or negative? Yeah, the centripetal force, the force pushing towards the center, is downwards. Because the center, when you're at the top of the circle, the center is down from you, so that force must be down toward the center. When you're at the bottom of the circle, Rachel, which way is the centripetal force? Sorry? Yeah, it's still acting toward the center of the circle, but the center of the circle relative to you at the bottom is upward, so we'd make that a positive force. Now again, we don't sub any signs in until we sub numbers in, but once we do sub those numbers in, it's important to include the positive or the negative with it. Sub in your numbers in at that point and solve for what you're looking for. We had 2 questions for homework last night. I think we want to do both questions. Do we want to do both? 1 and 2? Okay, let's do that then. Okay, question number 1 says, determine the tension of the rope at position A. So we've got our bucket at position A here. Gravity acts which way? Gravity acts which way? Reed, which way does gravity act when we're at the top of the circle? Good. There's also a normal force, which, by the way, in this case, is the tension in the rope, right? The tension provides the normal force. Which way is the normal force or tension acting when you're at the top of the circle? Down, right? Now, we don't know which is bigger. We're going to just make it around the same length. Could be bigger, could be smaller. We don't know. All right, we're looking for the value of Fn. That's fine. We're going to say F net, which is not Fn. F net is equal to Fg plus Fn. We're going to say F net is mv squared over r equals, well, Fg is m times g plus the normal force. And now we're going to sub in our numbers. M was 1.5 kilograms. V, you can see here, is 3 meters per second. And R is, what is the value of R there? 0.75 meters. M is 1.5 times 9.81 plus Fn. Now we got to start worrying about signs, positives and negatives. Gravity, which way is it? Liam, which way is gravity acting? Down, so we're going to make that a negative value. Good. Centripetal force, mv squared over r. We've got numbers subbed in for that. Is it going to be upwards or downwards? It's going to be downwards as well, yeah, because it's toward the center of the circle. So we're going to make that negative as well. If we calculate this force on the left-hand side, 3 squared is 9. 9 times 1.5 divided by 0.75 is 18. We get negative 18. 1.5 times 9.81 is 14.715 negative. We're going to take the 14 over by adding, and when we do that, Fn works out to be negative 3.3 newtons. Negative means it's acting which way? Down, right? Which it should be, right? We know from our diagram, we know from our logic that the normal force is acting down. Mathematically, we just proved that it's acting down because we got a negative value. Now, the normal force you can see here is 3.3 newtons. The force of gravity is 14.7 newtons, so the normal force is quite a bit less than the force of gravity. In this case, we talked yesterday about real weight versus apparent weight. In this case, the apparent weight, or the normal force, would be smaller, quite a bit smaller than the actual weight. You would be upside down. You wouldn't be able to tell you were upside down, but you would feel lighter than you normally feel. Right, Braden? Okay. All right, let's take a look at question number 3. It says a 0.98 kilogram rock is attached to a 0.4 meter rope and spun in a vertical circle. The tension of the rope and the rock is at the top. Tension of the rope is like Fn, right? Is 79 newtons down. What's the speed of the rock? Here's the rock. At the top of the circle, we have gravity and the normal force acting down, however big normal force is. We say F net is equal to the sum of the forces, Fg plus Fn, always. Now, if you didn't do this last night because you were struggling a little bit, that's okay. But come quiz time or come test time, we expect, this is one of those things we expect everybody to be able to get, at least to this point, because it's always the same. Next step as well. always the same. mv squared over r equals mg plus fn. Now we start subbing numbers in. M is 0.98. V, that's what we're looking for, isn't it? R is 0.40. 0.98 times 9.81. And the normal force is 79 newtons down. Let's worry about negatives and positives here now. The easiest one is the normal force because they tell me it's down. Make it negative. What about gravity? Gravity, Janae, which way is gravity when you're at the top of the circle? Down, so it's going to be negative as well. What about the centripetal force when you're at the top of the circle? Liam, which way is the centripetal force when you're at the top of the circle? Yes. So we're going to make it negative as well. Now, I'm still solving for one of the variables in that equation, but since I sub numbers into the equation, I'm going to worry about the sign, negative. All right, let's figure out some, let's simplify this a little bit and try to figure out what V is here. Let's say 0.98 divided by 0.4 gives me negative 2.45. Let's say on the right-hand side, negative 0.98 times 9.81. Now let's subtract from that 79. Gives me negative 88.6138. And let's say negative 88 divided by negative 2.45. 36, and then let's square root that, and we end up getting 6.01 or 6.0 meters per second. If you're going faster than that, then the normal force would have to be bigger. Okay? The faster you go, the stronger the string or the rope has to pull. Right? Kind of making some sense? All right. Let's go a little bit further here. Now, we know that if an object is moving in a circle, a vertical circle, if it's going fast enough, it'll stay in that vertical circle. But similarly, or conversely, I should say, if it's going too slow, it won't make it around the circle. Now, it's not like it's going to go to the top and then fall straight down, like Wile E. Coyote. It's going to follow to the circle, but it's going to follow to the circle in a little bit of a different path than straight down. We'll deal with that in a little bit. Bottom line is it won't make it around the circle if it's going too slow. How do we find out how slow is too slow? How do we find out what that minimum possible speed is that it takes to make it around the circle? Well, if it doesn't fall out at the top of the circle, if it does fall out at the top of the circle, it's moving too slow. You can see by my keys up here, let me cover this up so you'll watch again. You can see by my keys here that if I slow it down, at some point, you can tell where the minimum speed is, right? Now I'm probably minimum speed right here, right? It's barely making it around the circle. What do you notice about the string when it barely makes it around the circle? There's zero tension. That's right. So when it's going the minimum speed, the centripetal force at the top of the circle is sufficient, the force of gravity at the top of the circle is sufficient to provide the centripetal force. It doesn't need the normal force's help. If I go faster than that, gravity's not strong enough. We need the normal force to help it out. But if it's going at that minimum possible speed, gravity does the job, keeps it in the circle. Now, if I'm going below that minimum speed, not only does gravity do the job, gravity's too strong, and it falls out of the circle at that point. So the bottom line is, whenever you're solving one of these problems, where you're looking for minimum speed, we'll set it up the same way as we have those other questions yesterday, where the net force is equal to Fg plus Fn. But when looking for the minimum speed, We'll just cross off Fn because its value is 0. You'll calculate speed, and you know above that speed, you're fine. Below that speed, you're less than fine. All right, well, let's see exactly how we calculate the minimum possible speed. We've got a question here on page 262. It says, a 700-kilogram roller coaster full of people goes around a vertical loop that has a diameter of 50 meters. I don't like diameter because I want radius, right? What's the minimum speed that the roller coaster has to have so that the people don't fall out and that the roller coaster stays on the track? Here's the roller coaster. We know at the top of the circle. By the way, if it's going to fall out, it's going to be at the top of the circle, right? You're not going to fall out at the bottom. So looking for minimum speed, always analyze the top. Say F net is equal to the sum of the forces. We'll say Fn equals 0. Fn is equal to 0 because, well, at the minimum speed, the track doesn't have to do anything. Gravity does all the work at that one spot. F net is mv squared over r. Fg is m times g. Masses cancel. That's good news. If next Tuesday you get on the roller coaster beside a person who's 80 pounds, and then the next time you get on beside a person who's 300 pounds, you don't have to worry. The masses cancel. The minimum speed of the roller coaster is the same regardless of whether the person is 80 pounds or 380 pounds. It doesn't make any difference. Now, you're probably going to be a little bit more comfortable sitting beside the 80-pounder than the 380-pounder, but you're no more safe sitting beside the light person. It's exactly the same while going around a vertical circle. Okay, let's sub in some numbers here. We're looking for v, the speed at which the normal force becomes 0. The radius is 25 meters, not 50, and g is 9.81. Now, technically, there's a negative on both sides of this. The centripetal force acts down, and so does gravity. Now, that negative, it doesn't really matter where you put it, on the top or bottom. Here's what I'm going to do. I'm going to say negative 9.81 times negative 25. I'm choosing to put the negative with the 25. And that way I can take it to the other side easily, get rid of it. Becomes v squared is equal to 245. Square root that, and I'm getting v is equal to 15.6 meters per second. You go 16 meters per second, you stay in the loop, no problem. Although you probably get a little bit nervous as you're going around this thing if you're barely going the minimum speed, but you'd still make it around, no problem. If you're going 15 or 14 meters per second, it doesn't mean that you get to the top like this and fall straight down. It means that you get to the top and, whoops, not like that. You get to the top and fall out of the circle like that. Does that make sense? I promise I won't make you do this, but what type of problem would that be? A what? Yeah, one of the ones that took a lot of math, yes. What kind of problem is that? Somebody said parabola? It's projectile motion, right? Because it's following a parabolic path, right? Make sense? Now, it'd be a great question. I won't do that. Okay, it'd be one of those really challenging questions like I gave you with the inclined plane elevator / projectile motion. But you can see what at least it would look like. All right? All right, let's take a look at two questions that go along with that. Questions 1 and 2, page 262. Now, I want you to take special note of question number 2. It asks a little bit of a different question here. It says, not what is the min speed, but rather what is the max radius. Same question. Same question, just looking for another variable, that's all. If you're going too slow, given a certain radius, you'll follow to the circle. If you're going the same speed, but then they increase the radius, you'll follow to the circle. So in both cases, whether you're looking for min speed, as you are in question 1, or max radius, as you are in question 2, you're going to set Fn, the normal force, equal to 0, and solve for the variable that you're looking for, either v or r. All right, if we're good with those questions, then I'm going to ask you to take a look at the questions that are on page, lost them here. Here we are. Almost got them. Questions that are on page 268.